All right. Hey, everybody. So in this relatively quick video, we are hoping to prove our next big result in our series of results involving Chapter 7 about connected sets. And this theorem is a theorem that says that continuous functions preserve connectedness. And now what we mean by that is that if we have a continuous function f, and if we have a connected set S in the domain of f, then if S is a connected set, then f of S, the image of S, will also be a connected set, this time in the codomain. So to prove this, we actually want to work by contrapositive, which means that we want to try to show that if f of S, the image of S, is not connected, then S itself was not connected to begin with. So that will be our contrapositive statement. I will go ahead and write that up right now. All right, so here I've gone ahead and written up what we're trying to show with this contrapositive statement, right? So by the contrapositive, let me go ahead and make this full screen. Perfect. By the contrapositive, we're assuming still that f is continuous, but we're saying suppose the image of S is disconnected. What we want to show is that S itself is disconnected. And I've also written up what it means for the image of S to be disconnected. So because it's disconnected, what that means is that it can be written, this image set can be written as the union of two separated sets, A and B. And I can just sort of note that what I really mean by that is that this image set f of S is equal to A union B. Okay, and so let me draw a quick picture that might be useful, or just in sort of thinking about this. Let me choose a better color. So here's a number line, right? This will be my domain area D, and then I have my function f, and that is going into a codomain, right? Also a subset of the real number line, so I'll also draw it like this, but this is my codomain. Okay, and I have some set S back in the domain. I'm not going to worry too much about what that looks like right now, but I have f of S, the image of S, over here in my codomain. And what we're claiming is that I can write f of S as the union of two separated sets A and B, right? So maybe this is my set A, right? A itself does not have to be completely connected. It just needs to be separate from B, right? So maybe all of those three taken together, that's my set A. And then my set B here in bright green, maybe that's my set B. Okay, and then taken together, we're saying that A union B is equal to this image of S. Okay, now I essentially want to show that the same idea holds true for S, which is living back here in the domain. In other words, I want to show that f of S, that S itself, I want to show that S can be written as the union of two non-empty sets A and B that are themselves separated. And so what we'll actually do, and I think what makes a lot of sense to do, is to consider the pre-image of the set A and the pre-image of the set B, which will themselves be living back here somewhere in the domain D. So let me go ahead and draw that for us really quickly. Okay, and so here we've drawn our pre-images. We have f inverse of A and we have f inverse of B. Notice there's no real reason why, just because B was one component over here, the pre-image of B might be multiple components, and ditto with f inverse of A. So this is supposed to be a relatively general picture. But the idea is that all of these points over here are points that mapped into A, and all of these points here are points that mapped into B. Okay, great. Now, the argument that we want to make is that these sets, the pre-image of A and the pre-image of B, are the two sets that will show S itself is disconnected. In other words, what we really want to show is that F inverse of A, the preimage of A, and the preimage of B taken as a union is equal to S. So they make up all of S. We want to show that each of them is non-empty, and we want to show that those two sets are separated. If we can accomplish all three of these bullet points, that will mean that S is disconnected, which was our big goal, right? And it will mean that because S has been written as the union of two sets, in this case, preimage A and preimage B, it has been written as the union of two non-empty separated sets. That's exactly what we need to show that this is disconnected. Okay, let's think through each of these. First, F inverse of A and F inverse, well, first let's focus on this middle bullet point, because I think that will give us the first bullet point for free. F inverse of A and F inverse of B taken as a union is equal to the set S. Well, that makes sense because originally the set that we were looking at over here was equal to F of S, right? And what that means is that all of these points, I'll draw them in a neutral color. I guess purple will be our neutral color. All of these points, these were points of the set, sort of drawing it under the number line for emphasis, but taken together, all of these comprised the set F of S, right? Because originally F of S was written as A union B. What that means, though, is that these are the points in the image of S, right? And what that means, is that the points that map into here will be points of S, right? And indeed, every single point of S originally, wherever it was, got mapped into one of these pieces here. And so therefore, it must be in either the preimage of A or the preimage of B. So in other words, S is definitely contained in these elements over here. Okay. I think, so there's a subtle technical issue here that I don't want to overlook, but I also don't want to dwell on, which is that it's possible, right? We have to imagine that there's some element outside of S that got mapped to the same point here that maybe it's floating in here. And so that point outside of S might have been in the pre-image of B, let's say, right? This is because some functions aren't necessarily one-to-one, and you can map a point from outside of S into this image of S, and then if we go to take the pre-image of that set, that could also be contained in the set. So that's a small technical issue. What we can do to get around this is, and we probably should have done this from the start, I apologize that we didn't, we can, instead of taking F inverse of A and F inverse of B by themselves, I could take F inverse of A intersect S and F inverse of B intersect S. Right, so a small technical detail that just means that I'm not looking at points here. My red and my green points are not coming from elements that were not in the original S to begin with, right? So when we do that, then we're definitely guaranteed equality down here. And we do get, I should probably fix all of these. Every single one of these should be an S intersect. Okay, so unfortunate, small oversight there, technical issue, but moving right along, we get that every element of S must have mapped into the image of S. So every element of S must have mapped into here, which means that it either fell into A or B, which means that we are either looking at a point in the inverse, the preimage of A, or we're looking at a point in the preimage of B. So every point of S must be in one of these two sets. In other words, every point of S must be in this union. So this union is actually equal to S. Next up, For the same reason, we can basically see that F inverse of A, or the preimage of A and the preimage of B, are each non-empty, right? Notice that because A was non-empty, something had to be in A, and so some element over here has to map into A in order to make sure that A is non-empty, and therefore the preimage of A was itself not empty. Similarly, the preimage of B is non-empty because B was non-empty. So we've actually got the first two bullet points. There was this small technical issue, but we got the first two bullet points basically for free. And now the question becomes, are these two sets separated? That's a slightly more involved argument, so we'll tackle that next. Okay, and we're back. So for this final bullet point, again, it's a little bit of a more challenging argument, but it goes as follows. We can argue this bullet point by contradiction. So suppose that the preimage of A and the preimage of B were not separated. What that would mean, right, is that there exists at least one point in the intersection of either the closure of the preimage of A and the preimage of B, or the closure of the preimage of B and the preimage of A, right? So to be separated, we would need both of those intersections, the closure of one intersect the other, or the closure of the other intersect the first. We would need one of those to be non-empty. And so if we're assuming for contradiction that they are not separated, that means that at least one of those intersections has something in it. So without loss of generality, we are going to find a point in one of those intersections. We will assume that it's the closure of the preimage of A, intersect the preimage of B, and we'll call that point C. So C, I'm going to draw that in our sort of intuitive picture. C is going to be this point right here. Draw extra attention to it. That'll be our point C. And the idea then is that it is in B, I'm sorry, it is in the preimage of B, and it is in the closure of the preimage of A. So it's one of these green points, but it's in the closure of the red points. Now, our contradiction argument goes as follows. What that would mean then, if I were to plot C and see what was happening to C under the function f, then the claim is that that would have to land in, at the point f of C. So we'll call that f of C. And f of C would have to be an element of B, right? That's true because it was in the preimage of B, so it has to map to B. And f of C would have to be in the closure of A. Now, this in and of itself is a slightly challenging side adventure to show. We'll do that in just a moment. But once we've shown that, that would mean that A and B themselves would not be separated, right? Because if A and B, I should say, we initially assumed that A and B were separated. That's been one of our initial assumptions this entire time. So under this argument, we would have found that if F inverse of A and F inverse of B were not separated, right, then by contradiction, there would be this problem point, which would lead to this problem point, which would mean that A and B wouldn't be separated. And that's just a contradiction. So the final question is, why is this true? Why is f of C in the closure of A just because C was in the closure of the preimage of A? Well, this is true by corollary 4.30 and theorem 6.16. Now, theorem 6.16 is the sequential criterion for continuity, right? And that relates continuous functions to results about sequences. Theorem 4.30 is a result about sequences. It said that if an element, such as C, is in the closure of a set, that means that there exists a sequence of points in the set itself that converges to a limit, or that has as its limit this number C. So that was theorem 4.30. I encourage you to go back and double check it or reread it. But visually, drawing this under the picture, that means that there is some sequence of points in A that are marching towards C, and that their limit, right, if this is our sequence, this sequence, A sub n, has a limit, or I'll just say converges to C. So that's what theorem 4.30 says. It says that if C is in the closure, then this is guaranteed to exist. Now, the sequential criterion for continuity tells us something about what these image points, these a sub n's over here, I should say what their image is, the f of a sub n's will converge to. So let me clear some space in my picture on the right. So if I map all of those, right, those might be bouncing around all over the place over here, who knows, who knows. But if these are my sequence f of a sub n, the sequential criterion for continuity says that a function is continuous if and only if every time you have a sequence in the domain converging to some point, then the image of those points, that new sequence, the f of a sub n's, will converge to f of that original point. In other words, these f of a sub n's must converge to f of c by the sequential criterion of continuity, by 6.16. And then by using 4.30 again, we have found a sequence in the in this set that converges to, that I should say, in the set A that converges to f of c. Therefore, f of c must be in the closure of A. Now, worth just pausing for a moment to point out, this use of 6.16, this is the only time in the entire theorem where we use the fact that f is a continuous function. All right, so this entire theorem was a theorem about continuity and continuous functions. We knew that somewhere in the argument we would need to reference the fact that f is continuous, right? That's a fundamental hypothesis here. And this is how we're doing it in this single step right here. So a slightly technical sort of side argument here that directly references continuity and makes a play back towards sequences. But because we were able to prove this statement, that means we were able to prove this whole box, which means that f inverse of A and f inverse of B had to be separated. And that means we've proven our whole theorem. We assumed that the image of S was disconnected, and now we've shown that S is disconnected as well, because it can be written as the union of these two non-empty sets that are themselves separated. Awesome. All right. Thanks so much for this video, or thanks for watching this video. I'll see you all next time.